Welcome back. I'm Thomas Willingham. We're here with Christopher Chapman.
Hi again.
Networking fundamentals.
I like that, getting the hand in just the right place.
We're here to talk about understanding wide area networks.
Awesome.
So we've talked about TCP/IP, we've talked about OSI, we've talked about standards allowing devices to intercommunicate. Now we're going to talk about wide area networks, or basically expanding the reach and capability of our network. Our objectives include understanding routing. So routing is going from one network to another, and defining common WAN technologies and connections. Warning, this module has a lot of text in it, a lot of concepts, not as much fun graphics. Christopher's managed to throw in some fun graphics.
I got a couple.
But we're just going to talk about some fun foundational technologies, kind of overview them a little bit. So the first thing that we need to talk about is routing. Routing is a process of managing the flow of data from one network segment to another between hosts, devices, and routers. Data is sent along a path according to the networks, the IP addresses, and the IP addresses of the hosts. So think about it is where you have a map in front of you, you're at your starting point, you're trying to get to your destination, and there might be multiple methods or roads to get to your destination. How do you decide how you're going to get to your destination? You may pick traffic patterns. Okay, so I know on this road that traffic's going to be pretty heavy. I know that this road isn't as good. So I have one road with heavy traffic. I have another road that maybe it's not a decent road, so I don't like to use it. So there's two routes I am less likely to use than, say, a third or a fourth. Routing over the internet has similar ideas behind it. How many hops or how many routers have to be crossed to get to my destination? How fast is that line? How much degradation is there? These are issues that can be taken into account when it comes to routing. So the router is the device that maintains this information. And if we look at the graphic here, you'll see we have the fancy graphic that Christopher's done for us. We have multiple methods to get from our client to our server. So the client sends out a packet, it hits the first router. The router then evaluates from what it knows, its table of information, its router table, what is the best path to send it to. So it decides, okay, I'm going to send it this direction. This router then makes its decision, I'm sending it that way. The final router says, oh, okay, well, I'll send it to the destination.
What would help us determine, what would help a router determine which route to take? Because that diagram has a number of options on it. There are different routes that packet could take to get from A to B. So how do those routers know?
Well, and that goes back to the map analogy of trying to figure out a destination. There could be line degradation. A router port may be off. So possibly notice that the client went from the first router, and from the first router it went up instead of across. Across this line, maybe this line was down. Or maybe there's signal degradation, so it's causing problems conveying information across that. So that there hops, maybe the router's off, signal degradation. Those are all issues that could cause something to be rerouted.
Okay. That's something I can set manually if I want to?
You can. There is, and that's actually the next slide, static and dynamic routing.
Okay.
So with static routing, you basically configure a consistent path that's always taken. I'm always going to go from point A to point B to point C to get to point D. Dynamic routing dynamically configures the path that's going to be taken. So a static route, you have to go in and manually configure the route that's going to be taken between all the devices. The dynamic route, like I said, is configured, again, automatically. using protocols that the routers use to communicate with each other and communicate these routes. So if we look at the graphic, we'll see that this is a static configuration. So for each of these setups, these routers have manually been told. The first router was told, hey, if the client is going to that server, this is the route I want you to take. Versus dynamic, here we have a dynamic setup. Notice that it might take different routes depending on, let's show that one more time. It might take different routes depending on signal degradation, overload, maybe a lot of bandwidth is being taken on that, so you're not getting good response from that. So different routes can be taken.
Yep.
So dynamic routing. Dynamic routing has two conceptual parts to it. A routing protocol used to convey information about the network, and then an algorithm to determine what's the best path. And that algorithm is the road bad? Is the road overloaded? Is there bandwidth? That goes back to the traffic analogy.
Is there a road?
Yeah, is there a road? Maybe the road's closed. Common dynamic routing protocols, distance vector routing protocols. Distance vector is made up of 2 points, or 2 components. One, the number of hops to a network destination. This is the distance. And the direction a packet can reach a network, or the direction a packet takes to reach a network destination, which is the vector. So this is the distance vector protocol, routing protocol. Updates are sent at regularly scheduled intervals, and can take time for route to change or route changes to be updated. Link state routing protocols, updates are only sent when a route has changed. So this allows for routes where as a router goes down or as a network component goes down, when one of those events happens, then it sends out information. Versus the distance vector routing protocol and RIP, routing information protocol, is an example of distance vector.
Which we're going to cover in a few minutes.
Which we're going to cover. One of the issues with RIP is it's referred to as a chatty protocol. And it's called chatty because it sends out a lot of information frequently. So with RIP, it updates on a schedule. So it basically says, hey, I have a table, here's all the routes and networks I know about, and I'm just going to send it to everybody I know. The problem with that is as states change, that may be outside of an update interval, so it may take a while for changes to get propagated on the network. So route updates may take a while. Versus link state, and an example of link state is open shortest path first, OSPF. Link state, hey, when I have an update, this route has changed, I'm going to send an update. If the network's static and there's no changes, I'm not going to send any updates.
No need to be chatty.
Exactly. Or I'm only going to talk when there's a need to say something.
Yeah.
Interior gateway protocols. Interior gateway protocols are routing protocols that enable elements that comprise an autonomous system, AS, to exchange routing information. What does that mean? Well, for very large networks, it can ease routing to divide the network into smaller entities known as autonomous systems, or AS. IGPs, or interior gateway protocols, are routing protocols that exchange information within the autonomous system. RIP and OSPF are examples of IGPs. So notice here we have an AS, an autonomous system, and RIP or OSPF could be used within the system to keep the routers up to date about the paths. So here we have 2 separate autonomous systems. RIP and OSPF could be used in either one.
But they're not talking to each other.
No, they're not talking to each other. At least not with interior gateway protocols, they're not. RIP, Routing Information Protocol. It's a distance vector protocol, so basically deals with distance and I've totally blanked out on
Directions,
the word. There we
so
go.
to speak.
Distance and direction. Good. Thank you. That enables the exchange of IP routing information. The direction or interface is that packet should be forwarded to is calculated, as well as the distance. Each router maintains its own database of the number of hops to a network destination and the direction, so the distance vector. The nice thing about RIP is it's easy to implement. Typically, most routers, you can implement this by default, has a pretty large install base. One of the issues that we talked about is the fact that updates are sent periodically, so it's chatty. Open Shortest Path First, OSPF, is a link state protocol, and it monitors the network for routers that basically have changed their link state. A link is degraded, a port has been shut off, a route's no longer available. Once that information hits, then I'm going to send an update. The routers maintain a database of router advertisements called link state advertisement, LSAs. An LSA consists of router attached networks, their configured costs, and a cost could be number of hops, a direction, or maybe even a path. Maybe within your network, a specific path is a line that costs more to use than other lines do, so I'll use that line less frequently. And then finally, updates are sent when a route is actually updated. So we've talked about interior gateway protocols that allow communication within an autonomous system. Now we're going to talk about exterior gateway protocols that allow communications between autonomous systems. So exterior gateway protocols, border gateway protocol is an example of an EGP that enables autonomous systems to exchange routing information. BGP is used to enable routing on the internet. So basically we see these two separate autonomous systems that may use RIP or OSPF, it doesn't matter which, but they, before exterior gateway protocols, were unable to communicate with each other. Now with the exterior gateway protocol, bam, look at that. We have communication between the two of them. So now a device from one AS can get to a device on the other AS.
Absolutely. And it's all automatic. In theory, the whole practice behind these protocols, as we've talked about, as opposed to static, is you don't have to worry about it. You configure the routers initially, and you walk away.
And one issue that can happen, that can cause problems, is a router gets bad information. And so now all of a sudden a segment becomes unreachable. I have this network segment, I have devices on the segment, I can no longer reach that segment because the information about accessing that segment is bad.
Yep.
And that's an issue that people who manage routers have to deal with.
Possible.
So it's demo time. So now we're gonna, the royal we, meaning Christopher,
Royal we.
is going to configure an RRAS server and verify RIP.
I am. So we'd installed routing remote access in the last module. I believe the last module. And we kind of left off with that installing. It was actually in process. And that's now done. We still have our DHCP config, but that's it. We can now open up routing remote access through our tools menu in Server Manager and take a look at this console. And we'll look at how RIP is implemented once it comes up. There we go. So one of the first things you have to do with routing remote access is configure it. I'm not going to go greatly into depth on this. It's not set up in an environment that we could actually demonstrate routing, and that would take more time than we have here. But we will run through configuration real quick. I'm going to configure this as a router. It gives me options right away. In fact, we're going to see a demo later on of a custom configuration. For now, we want to do secure connection between two private networks. Demand dial connections, no. And that's it. Really all we're doing is we're telling the console what options we want to be available to us. This isn't configuring routing remote access with the options we need to actually implement this. What it's doing is giving me the tools. It's customizing the console. Starts, finishes, hopefully doesn't disconnect me, which is always a possibility. So that's up and running. So we now have routing and remote access installed and running. I have network interfaces at my discretion, so to speak. Ethernet, internal, and loopback. I have static routes. I can create static routes.
So this is where you would manually configure a route from point A to point B.
Yep, I've essentially turned this server into a router. I really, right now, it wouldn't work very well because it's only a single network interface that's connected externally. I'd have to add additional network interfaces and then using static routing, connect those interfaces to the networks, let the server know to what it's connected, and that's how it would work. There are a number of different options. General, IP4 router, IP6 router. And the remote access server, this is what's pre-configured by that option wizard. When it says, do you want to do VPN? Do you want to do point-to-point? These are the checkboxes that are checked and unchecked. I could turn this off and just do LAN routing only. We're not going to do demand dial. And then, that's all I need to worry about here. Yes. So it does the restarts. This is one of the tools that I like because Microsoft built restarts into it. I don't have to make a configuration change and then go in and restart the service and come back to it. And again, I can't configure static routes because I don't have that option. With only one network interface, we can't actually route anything. But yeah, this is where I would set that up. That's the easy part.
Okay, and then we would install and configure RRAS to basically implement wide area networking.
Well, I could use this for both. I don't know if we can get that slide at the last slide with the big diagram on it. I could use this for both the autonomous systems. I could create a router out of a Windows server within an autonomous system, or I could create that border router, so to speak, to connect to another autonomous system. Routing and remote access supports these protocols and can use them in either way, so we can use it for either role.
Great. Okay, so we've demoed routing and remote access. Next, let's talk about wide area networking. Wide area networks connect multiple local area networks together. Local area networks could include, say, a home, an office, a school, a building, a manufacturing plant, and then wide area networks connect these systems together. They allow networks to function without concern to location. WAN technologies can include packet switching. Devices transport packets via shared links. Leased line, dedicated point-to-point connection. Circuit switching, dedicated circuit path is created between endpoints, for example, dial-up. And cell relay, similar to packet switching, but uses a fixed packet length. So packet switching. Wide area networks utilize some type of packet switching technology. Services include X.25 and frame relay. Before packet switching, direct dial-up connections were used. X.25. Communications protocol was one of the first implementations of packet switching. You had data terminal equipment, DTEs, or a network device, connected to data communications equipment, DCEs, a modem, enabling communications to the X.25 network. So you see in the graphic, the DTE, the computer, connected to the DCE modem that connects to the X.25 network. Dummy terminals can also connect to the X.25 network using packet assembler, deassembler pads, which connect to the DCE. Virtual circuits. So telecommunication companies have thousands of shared circuits connections from which to select a path. These are known as a circuit set. The chances of an entire message taking the same circuit are slim. And when I say message, I don't mean one single frame. I mean, I'm sending a document. This document going down through the OSI model has been broken up into data and messages into individual postcards, and it's unlikely that those postcards will all take the same route. Remember, part of fragmentation of those packets also includes numbering. So as I get those, I can reassemble number. Depending on what protocol, I can look and say, hey, I'm missing 5. So I can respond and say, hey, I missed packet 5, please resend. And then this data transmission system is basically the core of core technology for the internet in most local area networks. So next we have hops. Hops are the number of routers that are crossed to get from source to destination. These stops, known as hops, as data is put on the X.25 network, they go through PSEs, packet switch exchange. There we go. I was missing the E. So packet switch exchange, basically like routers in the X.25 network. They go through the packet switching exchange network and get to their destination. Again, packet switch network, and a hop being how many times it has to cross a PSE to get from source to destination. X.25 advantages. If data fails, X.25 can recover and send it again. It allows shared access among multiple users on the LAN. So just think of as we were showing graphics earlier, a network, there's multiple paths to get from the source to the destination. X.25 has the ability to route between different paths. X.25 has full error and flow control, protection from intermediate link failure. Pricing is per shared packet set, not per minute, so per data. And the X.25 synchronous digital transmission, so there's less overhead per file. Frame relay is an advancement on X.25 packet switching. Standardized wide area network protocol using a form of packet switching designed for faster connections. So now we're basically picking up the speed. Also uses a virtual circuit, one that's a bit more advanced. Frame relay created the virtual network that resides in the cloud. Permanent virtual circuits. It's a virtual circuit established for repeated use. Frame relay enables multiple sessions to be run simultaneously on the same link. Connections to the cloud are known as permanent logical links or permanent virtual circuits. The PVC links a site together in the cloud, accomplished by using packet switching exchange.
Again, packet
Again,
switching
we're back
exchanges.
to the packet switching exchange. Leased lines. This is fancy terminology for the fact that you've bought a connection from a provider. So a client or a customer receives or purchases a connection from a provider. This connection contract is referred to as a lease line. Frame relay service must be purchased from an internet service or telecommunication provider. With frame relay, you must commit to a certain amount of information over time. This CIR, committed information rate, services the organization's account. But because the transmission is full duplex, there can be 2 CIRs for each PVC.
Lots of acronyms, lots of initialisms all of a sudden.
Yes.
This is the fun part of networking fundamentals. You get to learn all of the exciting topics all at one time.
And again, it's not important to memorize all this stuff. It's important to understand foundational technologies. So as you're talking to other network administrators, they're talking to you, they bring something up, you're like, oh, okay, I remember something like that. I may need to implement something like that on mine, so I know what direction to research.
And a lot of these technologies, one of the issues we're dealing with in building this course and teaching this course and other courses related to network fundamentals, not all the technologies we're going to teach you are current, are modern, are being implemented today. A lot of them may still be in use. That doesn't mean that they're currently being implemented. There aren't a lot of enterprises saying, hey, we need one of these right now, so let's get it implemented. But it's something you may come across. And unfortunately for this module, a lot of the technologies we're talking about are their wide area technologies are not something we can really do demos. So it tends to be a little bit more bullets and PowerPoints, and it just kind of happens.
A little more talking.
A little bit more.
Hopefully we're entertaining
A little more
enough.
just talking.
Yes.
Because we do lots of talking. We could do that all day.
Yes.
Yeah.
Hopefully we're entertaining enough that people still are able to gain information.
I'm going to
from all
hope
this.
so.
Hope so. T-Carrier overview. Additional wide area network technologies. Telecommunications carrier system for cabling. And interface system designed to carry data at high speeds. The basic transfer rate of T-Carrier systems is 64 kilobit per second, known as DS0. And they have different T-Carrier designations. DS1 is the digital signaling scheme for the T1 carrier.
T1s might be something that people have heard of, potentially.
People have probably heard of T1s, T3s. This is terminology we're still using that people should be familiar with. Okay. In North America, let's make that caveat that T systems are North American based. If you look at the graphic that we have here, you see the different levels of T carriers, the channels used, North America, Japan, Europe. Just notice that they're broken out a little bit different. Again, this is nothing you have to memorize, but it's a good idea to understand kind of how these work. Level 1, T1, is 24 user channels. The interesting thing is 24 times 64 does not equal 1544. It
does not.
There's a little bit of an overhead, and the overhead is basically for the channel overhead managing these 24 user channels. Notice that for the T1 system, Japan and Europe, they're pretty much equivalent. But then when we get to T3s and T4s, the number of user channels bundled is a little bit different. The US, North America, uses for a T3 672 user channels for almost 45 megabit per second. Japan, on the other hand, only uses 480.
I want one of those in my house.
For 32 megabits per second. And then Europe, 512.
I want a T3 at
channels.
home. Are those expensive?
I don't know. I haven't had to price that kind of stuff in so long. I don't.
They're probably
even
actually
know.
getting more expensive because competing technologies are so much cheaper that people stop using them and the technology becomes rare enough that, as opposed to getting cheaper because of demand waning and them trying to sell it, it becomes more and more obscure.
It's kind of interesting because it's interesting to note that sometimes older technologies become more expensive.
Yep.
Because as less people use them, they become scarcer, and because they're scarcer, it's a little more expensive. So another older technology, or a technology that's been around for a while, is ISDN, Integrated Services Digital Line. The interesting thing about this is it allowed faster communication speed than an analog telephone line, and it bundled it's a communication standards that bundled bundled in a digital manner, data, fax, voice, and video. So it bundled multiple systems. ISDN can be broken down into two major categories: basic rate ISDN and primary rate ISDN. The speeds are a little bit different, so what they can handle, the throughput that they handle, is a bit different. ATM, asynchronous transfer mode, cell-based switching technology as opposed to packet switching. ATM is a high-speed networking technology used to transmit data in cells of a fixed length, containing 53 bytes of information. It's a native connection-oriented protocol comprised of a number of related technologies for software, hardware, and connection-oriented matter. SONET. Okay, so now we're starting to get into, say, fiber optic. Synchronous optical networking. Standardized protocol allowing for the transmission of signals over optical fiber in North America. So for Europe, Synchronous Digital Hierarchy, SDH, is their standard. The nice thing about SONET is this represents a transport vehicle supporting data rates in the gigabit range. It standardized optical interfaces, networking management, and testing methods. Before SONET, companies were releasing their own hardware, their own specs that weren't compatible with other manufacturers. So if you started to buy fiber optic from one company, you were kind of locked into those, because if you bought fiber from another company, it may or may not be compatible. SONET was what basically standardized the system for fiber optic. SONET signal hierarchy, so this shows you the rates here, the level, the line rate, the channels. FDDI, Fiber Distributed Data Interface, standard for transmitting data on a fiber optic cable at a rate of around 100 megabits per second. Supports transmission distances beyond 50 miles. And when this first came out, this was amazing. People were like jumping up and down and really, really excited. Okay, I was jumping up and down and really, really excited.
Some people.
Well, I was all, woo, fiber optic, it's awesome.
This was right after we had port number quizzes.
Yes. Yeah. Then initially with fiber optic, you took your fiber optic cable, which is actually two cables bundled together. One is a send, one is a receive. You had to do the connection manually. You had to create that connection and hone and buff and do all that stuff manually. Wasn't a real exciting thing to do. It
Not
was,
the funnest experience?
No, not fun at all. It was interesting. It was a great learning experience, but was one of those, after you did it 2 or 3 times, you felt okay never having to do it again.
There are a couple of things like that in Network Fundamentals.
FDDI is a basically protocol used for backbones networks. And when I say backbones, there's cabling to devices, to individual devices, that typically runs data or runs information between that client and that server. But then you have areas of your network that carry data for large amounts of devices. And so these are referred to as more backbone. So servers, you may have your server on a backbone for high-speed communication between your servers. You may have a backbone between your servers and client switches, and then your clients go out using Ethernet. And then remember we discussed this was a previous module, fiber versus Ethernet. Although fiber's a lot faster, why don't I just use fiber everywhere?
Fiber is expensive and hard to work with.
True. So there's trade-offs with whatever technology you use. You hear of a new technology and you're like, oh, well, maybe I should make my whole network that. But there's the trade-offs.
Then you get online and you find someone to help you quote it out, and they come and take a look and they give you the quote, and you say, maybe we shouldn't make our whole network that.
DSL. So you had mentioned that there are some newer technologies that are coming online that are making the older technologies a little less likely and a little less used. DSL is one of those, digital subscriber line. It's a family of technologies providing data transmission over local telephone networks. Allows for voice and data to be run over the same line. DSL uses higher frequency bands to transmit data. Couple types of DSL. XDSL is the standard for just the various digital subscriber lines. Asymmetric digital subscriber lines. This is typical. This is what most people have. The upload and download speeds are different. They're asymmetrical. SDSL, symmetric digital subscriber line, the upload and download speeds are the same or symmetrical. This is atypical of, say, for home.
Yeah, most home DSL is going to be ADSL. Most of the subscribers out there that you'd see ads for on TV that, internet for $29.95 a month. Then you don't read the fine print that says for the first month, and then it goes up to $89.95.
Correct.
But it's usually asymmetric digital subscriber line, ADSL.
Yeah, and your download speed may be, say, 15 megabit per second, and then maybe your upload speed is like 4 megabit per second. So there's a disparity between the download speed and the upload speed.
Yep.
And then depending on what you're doing, that may not matter. I mean, if you are a consumer, so you consume information off the internet. So you're looking at web pages, watching videos, looking at documents. You're less concerned with upload speeds.
And most people are consumers. That's why they have those. The asynchronous allows them to actually provide the service cheaper, so that the majority of people who are consumers can get that service for a little bit less cost.
But then if you're a content provider, a business that's uploading content, YouTube, they're showing videos, then you'd need a more synchronous system.
It's not so much that they need to be in sync. It's just that you need more outgoing bandwidth. So you're going to pay more to get that upload speed up to where your download speed is, just for that functionality independently.
Correct. So DSL, there's also broadband cable. So DSL is over phone lines. Broadband cable, those are your cable providers. So now you have the ability to have internet and cable television using the cable television network. So previously, we've talked about digital lines versus now I'm blanking out on the word again. Analog, thank you. The digital clock, it's one discrete thing to the next discrete thing. Analog, I thought of another great example for analog, a golf swing. A golf swing, as you swing back, so see, there's something for everybody here.
There can be.
So I'm throwing something out for golfers. So now, you may be a golfer. Golfer swing is analog. As you bring that back and then swing the club, I have stuff in front of me, so that was by no means to be a demonstration of a decent swing. As you come back and hit, that club can be any of a range of motion. Versus a digital clock is a discrete time until the next discrete time. So those are good examples of analog versus digital. In an analog system, you can use any of that area, so you can basically use different frequencies to create different channels, to create different signals, broadband cable. So you can have television running at one frequency, you can have your cable running at another frequency, and then you have different boxes that split these frequencies out. We're going old school now. Earlier I talked about
I know exactly.
Telephone.
It's funny you say that, and I already know what the next slide is. I don't even see it. I don't have it up in front of me. So he says we're going old school. I know exactly what he's talking about.
POTS and PSTN. Plain old telephone system and public switch telephone network. This is your regular phone lines. Been around since the 1940s. Now, digital at the switching office and some central offices, but there are still analog lines that run into people's homes.
There are a couple of those still out there in the world somewhere, I'm sure.
There are people who still have analog phone lines.
Who have phones, like telephones that don't go in your pocket when you leave the house.
Right. Yeah. Okay. So we're at the summary.
We're always at the summary.
So we're at the summary. I'm not really sad this time. Normally I'm sad. We hit the summary. I'm like, oh, we hit the summary. This time I'm not sad. I mean, don't get me wrong. WAN technologies are important. It's important to understand these WAN technologies. Honestly, you don't really use it.
Well, the module is not that exciting. There's some good stuff. There's some good info. There's a lot of us talking.
There were some great graphics.
I couldn't make the great fun graphics I've made. No servers saying hi to each other. It's just a lot of info. And yeah, it's older info. So it's important. You'll want to know it. Have it handy for the cert, for potential employers, or for potential opportunities where those technologies are in use. They are good to know and have in use. But not our most exciting module.
No.
But now you can go to the next one, because that one's more exciting.
It is. Well, okay, so actually, I take that back. There were a couple exciting components, static versus dynamic routing, and talking about routing. Routing's kind of exciting.
Yes, routing is.
It's nothing that you deal with on a day-to-day basis, but just conceptually, it's interesting.
Someone might.
I find it interesting.
Someone might deal with it. Routing is one of those things, of all the things in this module, routing is one of the topics that somebody may actually end up doing that. There are administrators who manage routing, and that's what they do.
Right. We talked about RRAS, Routing Remote Access Service. That's kind of interesting. Saw a little demo of it. Things and stuff.
Yeah, things and stuff.
Yes.
Yeah,
good times were had there. Our additional resources and next step slides.
Yep. Once again, the book, 98366 MTA Networking Fundamentals, the Microsoft Official Academic course. Our 4 instructor-led courses, the bottom one, 40366A, is specifically the Networking Fundamentals. The other ones are packets of other courses along with this one, or good accommodating courses to go along with this one. And then the exam certification, what you're here to learn for, 98366 Networking Fundamentals, to get your Microsoft Technology Associate certification.
And the end slide.
That's it.
Yeah.
That's all we got.
Well, okay, not quite it. What I would say is, if this is the first module that you've watched, watch another one. Don't judge the modules by this one. This one's a little dry. You're laughing.
It's
not.
No, it's true.
It's true. This one is a lot of talking. It's a lot of standards. As we mentioned, the technologies may be a little bit older. It is important to know them. They are foundational technologies. Watch another one.
Yeah.
That's all I got to say.